C's get degrees.
Yeah, C's get degrees.
I don't care. I don't have to take that class again. I don't really care what I passed it with.
Okay, that looks good. All right. So let's see. We got some problem.
That's just
T's, huh? Okay, good.
Christian's got more.
Oh, look at him flying through this. Okay, that's probably good there. All right. So we'll get to those in just one second.
It's crazy.
All right, so remember chapter 5 was integers. Other term for integers could be signed numbers. So just do a few basic facts about those, then we'll start playing with some toys. So let's see, where did the integers come from? Well, we started off, remember, with counting numbers. 1, 2, 3, 4, 5, and then we decided we needed 0, so that's called what if I throw in 0? Remember? So count whole numbers, yeah, throw in 0, you get a whole in it, those are the whole numbers. Then from the whole numbers, we make the integers, and the integers basically come from the idea, at least one place they can be said to come from, is we can do 4 minus 3 with kids really easy with whole numbers. That's 1. But the problem happens when we try to commute that and say, what's 3 minus 4? Now all of a sudden we don't have a number for that, and so that's where the integers come in, because we want an answer. And we're going to show in a couple different ways that the answer has to be what we call negative 1. And so that number is often read negative 1. It can also be called the opposite of 1. And something about opposite in math, there's a few different definitions of what opposite means, and we talked about that a little bit at the end of last term. Doesn't look like opposite has 2 P's. I think. Here we go. All right. So what does opposite mean to you? Think about that for a minute before you say anything. What does opposite mean to you in the context we're in here? Think about that. Anybody want to tell me how they would describe opposite to somebody?
The other side of the scale.
Other side of the scale? Other side from what? How do you get
Like
to the
a
other
number
side?
scale.
A number scale?
So if you're at 1, you go to the left.
So this is 1 over here.
Go to the left, you're at 0, then you're at 1 again.
Okay, so the other side of 0 is where I get negative 1. Yeah.
But wouldn't you have to say something like the same number or something? Because kids are going to be like, oh, well, the opposite could just be any number on the other side.
Any number on the other side. Yeah, okay. So yeah, so how do we talk about 1 being paired with negative 1 and 2 being paired with negative 2? Okay. So we can clarify that.
Same number, different sign.
Well, we don't want to be careful. Remember how we used the word number last term?
Yeah.
Number is that abstract idea of how many. Right? So what's a different word we could use? We call it units, or distance is what we usually say. Because like I don't really care whether I move. That's 1 unit to the right. That's 1 unit to the left.
Oh, so like maybe the same distance from
Yeah,
0?
same distance from 0, but other side. So that's one definition. Now, I almost wrote a different word besides other there. What other?
Opposite?
What's that? Yeah, I almost put the word opposite there. What would be
but
wrong
we're
with that?
describing it.
We're describing opposite. We shouldn't use it in the definition, right? That's bad practice. What's that?
Oaths.
That's it. That's an O. Attached to the either.
That's an R.
Yeah, it's the rest that gets squeezed in. This guy. Leave it out. Okay, so that's one way to do it. Often, opposite is described, so negative 1 can be read negative 1 or the opposite of 1. In math, that negative symbol is usually defined as a negative 1 times whatever comes next. So the opposite of 1 is really negative 1 times 1. The opposite of 2 would be negative 1 times 2. So that's another way we could define.
Oh, so it's negative 1 times.
Yeah, so the
Anything
negative
with a negative
symbol
number.
means negative 1 times.
Oh, okay.
Right, so
So you could do it all the way up to whatever.
So you can do it with any number you want. Yeah. So this negative symbol right there means negative 1 times. This negative symbol right there again means negative 1 times.
But is it for a whole number to the right of the 0, or could it be a negative 1
It could be
times
for-
a negative 2?
It could be anything. So for example, I could use that to talk about the opposite of negative.
So negative times a negative is going to be a positive.
The opposite of negative 2. So what would that look like? Well, we could put two opposite signs together like that, which looks kind of weird. Usually we put parentheses around it if it already had an opposite sign in front of it, or what we call the negative sign. And again, that just means negative 1 times whatever comes next. And what does that negative sign right there mean? No. It's negative 1 times this right here. So really what that means technically is negative 1 times. That also means a negative 1 times. And then finally there's the 2 there. Now, there's a couple reasons why it's defined that way in math. One reason is it kind of boils down to every time you need to multiply two negatives together, it boils down to what the heck does negative 1 times negative 1 mean? And yeah, we believe it means 1, but why? So that's one question I'm going to try and answer today. Why is negative 1 times negative 1, 1? So that's an important question we have to answer. Are kids going to get the why when we first start doing that? No, it's a weird technical detail. They'll just accept it. Oh, okay, it's 1, cool. Right? But we as teachers, we should have a couple of ways to understand why that works. So what do we usually use when we're trying to figure out why? In this class, in previous classes like this.
How's it why?
A model or an algorithm?
Both.
Model.
A model. Good job. A model. Yeah. So a model tells us why something works. An algorithm just works. We don't really care why. It just works. So we need to come up with some kind of model for integers to justify this. So does anybody remember any of the models we talked about at the end of last term? Charged particle 1 was 1. Remember any others?
The consult book.
I know we did arrays, but the
What's that?
array.
Array was for multiplication of whole numbers.
Oh.
So here we're just saying model of an integer, not really worried about add, subtract, multiply, divide yet. So the charged particle was 1.
Oh, number line.
The number line was the other one. Yeah, number line was the other model. Okay. So those are the main two that we use. And the charged particle one came up in a couple of different ways, either dealing with chips or pluses and minuses. Okay. So I brought some toys to play with that way. So let's take a look at the charged particle model for integers. Check something. Yes. So charged particle model for integers. So I'm not worried about addition, subtraction, multiplication, or division yet. This is like activity 1 in the workbook. It's in section 5 we did before. So the idea was we had positive creatures and we had negative creatures. And there was one other creature we had to have. Does anyone remember? The other creature we had was in our key for this model. Positive, negative, and 0 is the other thing. 0. So we have 3 things in our key. when we played around in class, we use these little flip chips. They come in a lot of different colors and classrooms. Results graphs here. Okay, so the next job is to glue these together to make one of those.
Give me a lighter.
There. Okay. So we have the flip chip idea. And does anybody have the workbook in front of them? Here, trying to remember what they did in the book for this one. They said the light chips were negative, dark chips were positive. So we use red as positive. So with our toys, these were red chips. The workbook's black and white, so they called them dark and light. And so a red chip would look like this, maybe a dark chip. Red, dark. Is that what it is on a car?
Huh?
Why should red be negative? Did you say that?
Yeah, because each time you see red, just think negative.
Yeah, that's what teachers always use. Is
That's why you don't use red pens.
What is it on a car? Can you remember that? Dark. Black is, so that's positive. Okay.
I don't jump with that off, please.
All right.
I
And
know.
then the lights chips are, I draw them like that. And then the thing is, well, how do we represent zero? And so the idea with the charges is a positive and negative charge cancel each other out to be no charge. And that's what zero is. So zero is no charge, which can also be written as a dark and a light chip together. So the interesting thing about this particular model for integers, there's other models for integers, we'll get to in a minute, is that that means there's multiple ways to express any particular number. So if somebody said, well, use this to represent the number 2, well, I would say, okay, here is the number 2. Because there's 2 dark chips. Positive 2. On the other hand, I can also represent the number 2 by doing this. Why does that also represent the number 2?
Yeah. Because you cross them out, so there's like
Oh shit, sorry, I meant to color that in. All right, now, there we go, now. Oops, why is it now 2?
because one cross you.
Yeah, those cancel out to be a 0, so the net charge here is positive 2. Okay? And we could do that all day long. This right here would also be a charge of positive 2. Now that is both a problem and it's also a blessing because it's going to allow us to do some tricks with justifying why certain addition and subtraction problems work out. So we'll do that. So there's no unique way to write a particular number with this model, but it's going to give us some power later. 0, so again, that's 2, that's 2. 0 could be that set right there with nothing in it, or 0 could be any set with a positive and negative or more that match each other to balance out. So there's a ton of different ways we can write any particular number. So just for fun, on your paper, show -3 in 2 different ways.
Two different ways?
Yeah. Let's see. Still not good. So those are the easiest 2 ways I can come up to represent -3. I'm having one of those guys too.
Don't.
We're still on vacation.
Oh yeah, you had like a deluxe vacation. What was that again?
Cancun.
Oh my gosh.
It's fun.
You didn't get very tan.
Hey, I got food.
You got burnt. I tried something crazy. I tried snowboarding.
Oh, yeah, how about-
Snowboarding before.
Oh my gosh.
I felt like I was in a rear-end collision. I didn't break anything or damage anything permanently, but
I love
wears you
skiing.
out.
I was hurt.
I
You like ski?
Oh,
I just skied for the first time last year. And so a friend of mine said, oh, you should try snowboarding. That's way better."
Snowboarding's way
You didn't
Are you
play
trying
Sunny
either?
Bonos, did you?
What?
You didn't play Sunny Bonos, did you?
What's that?
You didn't run into the tree.
Oh, no, right. Sunny Bono. Okay. Didn't he like turn into a vegetable after that?
Did you go to Anthony?
I went to Anthony one day and Spout the other. So I've done snowboarding.
Definitely do skiing. It's way easier.
Yeah,
You
that's what
need to have control of both.
I
ways,
skied
you know?
maybe 10 times last year, and I snowboarded twice. And I got 10 times more beat up snowboarding.
It's hard.
I used to ski race.
You did?
Yeah.
Oh, I'll probably keep it.
No, I went to a different ski hill, Bluewood.
Oh, I haven't tried that. Okay, so back to sign numbers here. So we have many different ways. Now notice that there is a way to do it with the least amount of toys, right? What's the least amount of toys I can use to represent -3? 3. What's the least amount of toys I can use to represent 2? 2. What's the least amount of toys I can use to represent 0? No, right, yeah. So the worksheet in section 1 we did last term asked that question about the least amount of particles. And that idea of least amount of particles translates into a mathematical idea called absolute value. Does anybody remember how they thought about absolute value, like from an algebra class? Rounded. The bars around something, right? So we could do something, right? Bar, -3 bar. Did I ever tell you a story about the absolute value of 0? Does anybody remember that from last term? So I was teaching like one of my first classes through an interface like this where there's people somewhere on the internet, there's people in class. And I was doing math and somebody wrote back. I wrote back, like, why do you want to know about the absolute value of 0? That has nothing to do with what we're talking about. And they wrote it again.
It's LOL.
Well, I never texted, I didn't have a cell phone at the time. And they kept writing that and everyone in the class laughed.
They literally are laughing at that.
Yeah. So here is the absolute value of 0. So absolute value of 3 is 3. Absolute value of 0 is 0. And how would you describe the absolute value of 3 to somebody besides, forget about the charged particles? How would you describe it to somebody before? How to tell some kid how to find the absolute value of 3 or the absolute value of 2?
The car wash.
Car wash.
The car wash.
Tell me about the car wash.
It goes in dirty, which would be the negative,
And it
and
comes
it
out
comes
clean.
out clean.
Oh my gosh, negative numbers are dirty. So I'm having a hard time with that analogy.
And filthy.
It's cute. It's still cute. Okay. Any other thoughts?
Well, technically, you couldn't put 0 and it comes out of 0.
It's clean. It's clean to begin with. It's clean.
It's just cleaner.
It's just cleaner somehow.
It's a clean number.
Shinier.
I would just say just drop the sign.
Okay. So how would I deal with like the absolute value of 2?
That'd be 2.
That's 2. So how come that's 2 and that's 3? Like that lost a sign. Nothing happened to that one.
Because it went in clean, so it came out clean. It's just like if your car's clean, you take it to a car wash system.
Okay. So let's see. That works. I can do with the car wash thing. Let's see. One thing we're very fond of in math. Oh, there it is. We love our number lines. Like, I haven't been in an elementary school in a long time that doesn't have a number line and pasted to the desk somehow. So how could we talk about absolute value on a number line? Because that's our other model, right? We have the chip model, we have the number line model, charged particle model.
Does it also look at the distance?
What is it?
The distance,
Between
equal distance. After
Distance, got distance, a little more distance. Well, it's my time.
from 0.
From 0, yeah, distance from 0. Right, isn't that how we talk about it? The absolute value of -2 is 2 because that's the distance to 0. So I wouldn't say go -2 miles to my house, I'd say go 2 miles east. If west was possible, right? Which it is because we live near the West Coast, right? So distance from 0. And we kind of use that to talk about opposite too. So that's popular. So the number line model is pretty pervasive in a lot of curriculum, and you'll see that all over the place. But you will start to see this charge particle model around in a lot of books. And sometimes they'll use chips. Sometimes they call it the chip model. It's the charge particle model, the same thing. Alternatively, we could talk about charged particles by using charges, like a plus and a minus. So this right there would be positive 1, and this guy right here would be negative 1. And those two together are one way to represent 0. So with that in mind, I'm going to hand out. Now these you're going to have to share because I didn't get to do enough ahead of time. So you guys can share some of those. Right. That's negative, that's positives. And let's see, let's see. That group. So, by the way, the white residue on this is nothing dangerous. It is only tiled grout. These are from tiling project in the house. It's not toxic, just don't eat.
So you made these?
What? No, so I went to Vimarks and I bought these for $2. And there's 250 of them. And all I have to do is either do it myself or hire a slave to cut off the ends and turn some of them into negatives. And then you have a cheap way to create your own charged particle set for your classroom.
Or you just announced someone to volunteer?
Yeah, right. That's what I meant by slaves. Volunteer slaves. Okay, so pros and cons, right? Some school districts have all kinds of toys ready for you to get that share among classrooms or in a particular classroom, which is cool. Sometimes your ESD will have these toys you can check out. Maybe your school has a budget and you can buy some of those chips. So my recollection is a set of these, like this packet's like $5 or $10. And this packet at Weimar at 250 was like $2. So cost, pretty good deal, a little bit of labor, not a big deal. And homemade manipulatives can be fun. And you can find other ways to make them. Creative ways, maybe like an art project with kids. Anyway, I kind of like the charged particle model better for a couple of reasons. I occasionally get confused about which color is which. With me? Shit, which one is positive again? Oh, I get it backwards, and that can cause me grief. And there'll be kids that have that problem, like kids that struggle with left and right. Like I'm one of those kids. These, on the other hand, we talk about a number being positive or negative, and we use these symbols. So that's one reason I really like playing with these toys. All right. So here's a slightly different version of the charged particle model with actual pluses and minuses. So now we're going to just jump into adding and subtracting. So let's do adding. What do you call that model? This is the charged particle model. Yeah. Yeah. So sometimes you'll see it come up in books in different ways. Sometimes it's always called the charged particle model, but they'll use colored chips. Sometimes the charged particle with chips is called the chip model, which is kind of weird. Color chips, which it works. I mean, it's totally fine. And so it just kind of depends on which book you use. But this is still the charged particle model with slightly different representations of the charges. So we know what signed numbers are, integers. Okay? It's some number of positive chips or negative chips or 0. What does addition mean?
Put together.
Yeah. So our set model for addition is put together, or combined. Okay. So back from using whole numbers, we had the set model, and the set model is just put together. That's also known as combined. So if I take the set model together with the charged particle model, I can then do addition with integers. So just a reminder, I kind of have to have a key to pull this off. And my key is, what does it mean to be positive? What does it mean to be negative? And what does it mean to be zero? Similar thing to using the colored chips. So let's just try that. So let's suppose I wanted to do -2 plus -3. So then I whip out my charges. I show -2. There's -2. And then I want to combine or put together with -3. And so after combining, I get that new set there, which I could call what? You call -5. Doesn't look too much different than taking 2 plus 3. We just need these toys to demonstrate. Now it gets more complicated when I want to throw a positive integer and a negative integer together. So let's suppose I had -5 plus. So -5, what does that look like? Well, 5 negative charges in some arrangement. I need to combine, because I'm adding, with +3. That gives me a new set. That might look like this. So then the question is, after I combine, so there was one catch on addition of integers. It was combine and count. Yeah, we had to actually count to figure out what the total was, the sum. So how do I count this up to come up with a total? Or should I do next? Yeah, some of these are zeros, right? So we could identify, hey, that's a 0, and that's a 0, and that's a 0. And so finally I can count and name this as, this has to be -2 as the sum. And then we could do a whole bunch of these with the kids. And then we could ask, like some kids might say, hey, wait, I could write this a different way. Can you think of another problem with 5 and 3 you could write down that gives the same answer?
3 minus 5.
Yeah, this is really the same thing as 3 minus 5, isn't it? Because that also gives me a -2.
Because it's like plus -5.
Oh, we could rewrite this as 3 plus -5? What gives me the right to do that?
Nothing.
You're adding a negative number.
Nothing gives me the right to do it. No, there's a reason I can switch those.
Addition.
Oh, the
Yeah, Greg, high five. Addition is commutative. Yeah, addition has the commutative property. So some properties from last term, we talked about commutative, associative. So just a reminder, commute, let's see, how many people commute from school to home? Nobody lives here, right? We all commute. To do that, you got to move, right? So commute means to move. The numbers physically move. Now, as far as associate goes, the way these three are sitting in front, Hillary could either associate with Brittany or with Kelly, because they're next to each other. Nobody has to move, though, right? You can just look over whisper her, you can look over whisper her,
So it's
no problem. That's association, yeah. Association, you don't move anything, you just choose to associate to the right or to associate to the left, and that's when we shift parentheses. So just a reminder, this is slightly off topic, but something like 2 plus 3 plus 4. Order of operations says we should do it left to right and add those two first. Because addition has the commutative property, we could choose to have the numbers associate that way instead. I don't move anything, I just change the order I do them. So associate just means kind of like communicate with, talk to. Commute means physically move them. And just something to note, we'll come back to that later. All right. So the point here, this is really an addition problem, not a subtraction problem. So we need a whole nother way to deal with this, but they do happen to have the same answer, don't they? And that's just something interesting to note. And some kids will figure that out after doing a bunch of these. Others, you need to point it out to as we move along. Let's try another one. So how about -3 plus 4? So if you could draw a model to demonstrate what the answer should be with the charged particles. So we can demonstrate after we regroup and pull the zeros out that this is the same as 1. Now, remember, we're way too familiar with algebra. How many people look at that without this model and just think, oh yeah, that's 4 minus 3? Anybody here think that? You look at it? This one person raised their hand, we get some nods. So again, we're familiar with that. Now, it's not obvious to kids why. We could just say, hey, this is the same as 4 minus 3. But we need to work up to that somehow. And charged particle model is one way, number line model is the other way to do that. Let's take a peek at subtraction next. What subtraction model might work well here? I think we had 4 subtraction models last term. Takeaway?
Subtraction means takeaway.
Yeah. So that's one model that we can do.
Adding method.
What's that?
Adding method.
That is not a model, that is an algorithm. So we'll get to that. What other models did we have? Anybody remember? Comparison model was another one. Yeah, what else? We had 2 other models for subtraction for whole numbers. No, that was an algorithm. Yeah, I know, it's hard to keep track of all the algorithms and models. So remember, model is Y, not X, which we use for small numbers to get the point across. And then we start working with number line was another one, yeah. And what was the other one? Can you remember? Notes, jog memory. The book had one name for it, I have one name for it. The book called it the missing add-in model. I called it the what do I add model. So that was our other model. And it turns out any of these will work. Some are easier than others. I'm going to focus on the takeaway model. So takeaway, again, that's physically remove. And so just reminder, I could show 5 minus 3 by saying, okay, I have 5 things that could be pluses. And then subtract means take away 3 of them. And that really is a positive 3 sitting there, right? And taking away a positive 3. So that means I have to take away 3 pluses. Sure. I'll take that one, and that one away. That leaves 2. Boom, done. No problem. Here's where it gets interesting. So we have our key. That's a positive unit. That's a negative unit. And then 2 of those together is one way we could write 0. And we're going to interpret subtraction as takeaway. So what if I wanted to do something like 5 minus negative 2? Okay, so that says from 5, so there's 1, 2, 3, 4, 5. I have to take away 2 negatives. Probably. Any negatives here? Oh, well, what could I do?
You could add them and add more positive.
Yes, I could make some zeros, right? So I could say, well, you know, that's still 5 net charge, right? Because these 2 right there I just put in cancel out. Do it again. That's still 5, isn't it? Net charge. Now I'm in a position where I can take away 2. Yeah, negatives, that is, yeah. So now, so I had to rebuild with zeros. And so now I can take away those negative 2's. So these 2 go away. What does that leave? That leaves 7. Now, Christian mentioned the idea of adding the opposite. Right? So I think you were saying rewrite this, question mark, as 5 plus the opposite of negative 2. What's the opposite of negative 2? Positive 2, which also leaves 7. So the question is, well, what gives you the right to rewrite a subtraction as adding the opposite? Whoa.
What I just said?
You said a negative plus a negative is a
Oh,
positive.
no, 7 negative times a negative.
There's multiplication going on here?
Well, I see parentheses, yeah.
So do parentheses always mean multiply? The answer is no, because here what I'm doing is I'm subtracting. There's no multiplication with this set of parentheses right here. It's just a separator to distinguish those 2. A lot of times, instead of parentheses, some textbooks, some curriculum, will write it as a 5. A minus is a lower long bar, and a negative is a short superscriptive one. And so they might view it like that. This is 2, 1, 5, and 2. So there's another way to write the problem without. So the bottom line is the idea of subtracting is different than the idea of taking the opposite of something. Subtracting, I'm ripping away. Opposite, I'm jumping to the other side of the number line. 2 different physical mathematical ideas. Do we use the same symbol for both often? Yeah. Is that easily confused? Yes, totally. And so we need to try and use language carefully. This is subtract. This is the opposite. What other words do we use instead of subtract?
Minus.
Yeah, we use the word minus. Subtract. What else do we use?
Take away.
Take away. That's pretty common. this symbol right here, which is a different color. So that is, I'm calling it the opposite, right? What do you often call it instead of opposite? Negative. What else do you call it? No, you never call it that. Sorry, you may, if you do it. So no, so if you just saw this number sitting on its own, would you say subtract it 2? What would you? How would you refer to that number?
-2.
You would call it -2. What else would you call it? That's it. -2 is the only thing you call it. Nothing else comes to mind. You just call it -2. Those are no fun. What is it, Kelly? Would anybody look at that and call it -2? Have you heard people call that -2? I bet you have. You haven't, Adrian? Never? You sure? Positive? Not that comes to mind, but maybe somebody you blocked it out. Minerva, have you ever heard it called -2 sometimes? Yeah. So I mean, so what's the problem here? Well, the problem is we as human beings are very loose with language. We use words, to mean different things, and if we're in the right context, everyone's like, yeah, I know what you mean. Right? So if I say this is -2, you'd be like, oh yeah, I know where that is on the line. If I said this is 5 minus -2, you'd be okay with that, right?
But you can't say
Could I say that's 5 minus -2?
Yeah.
Sounds awkward, but I could say it. 5 minus -2. Wouldn't be, yeah, okay, so it's politically correct math. That's a good point. So my point is, as a teacher, we have to be careful when we use language, especially when people are learning these things new. In common language, we might throw out terms and, in context, we'll get it. With new math topics, we need to be super careful about those. So one thing I would try to do is not use the word minus. Because some people use it to refer to subtraction, some people use it to refer to a negative number, and some people use it for both. Some people never use the word minus. Like Adrian, I don't think ever uses the word minus. He's like, nah.
Well, I have, just not as a negative.
Okay. But with subtraction, maybe? Okay.
I would say 5 minus -2.
Yeah, okay, and I say that too sometimes. Yeah. So, but sometimes we have to remind ourselves, again, this is a new idea, they're getting used to these words. I should choose my words carefully when I use them. Because otherwise, then people get the belief later that, oh, a minus sign and a subtraction, they're exactly the same thing. But they really aren't. Subtract means physically take away. It's one interpretation of it. Whereas minus just means either a place on the number line or go find the other side of the number line. And think about, anybody have a calculator on? On your phone? What about a calculator? How many people's calculator have a subtraction key and a minus key? Right, yeah, because the computer, they're two physically different things. They're not the same thing, right? So we got to think about that as teachers. That's a subtle thing, like we take for granted. We're just used to dealing with it. Right? We're just used to dealing with it. So one thing these models do is they serve two purposes. One, they give us a way to kind of build up a game that shows why something should happen the way it does. Alternative, it is because I said so. Well, why, teacher? Because it is. Now just do it, right? And that's the way most of my math education was. It's just, why is a negative times a negative a positive? Well, the teacher said so. Why can't I divide by 0? Because the teacher said I could, and my calculator freaks out when I try. But there's a reason. All right, so subtraction is a bit tricky. Let's do one more subtraction. All right, so I want you to try and write this down. How about -3 minus 2? So I would like you to model that with charged particles. And then I want you to actually build it with your little charged toys in front of you.
I'm so confused.
Oh, did I not give you guys any negatives?
We have no
I
negatives,
didn't
it's all
steal some from
positives.
Greg.
It's okay. We got that.
They stole mine. They stole yours, okay. These are the same size if you don't know that. That is a cute pink laptop.
Thanks.
Is that yours? Matches your face too.
I hate but
You hate pink,
yeah,
but you have a pink laptop.
I was looking for that.
Okay.
She was.
Okay. So I'm kind of showing two frames here of how you would work with the toys. I wouldn't have kids write down both of those steps. I would just have them do it. Right? Like you just set with 3 negatives in front of you. And Kelly's like, hey, wait, I can't take away +2. And then she says, oh, but I can, there's some zeros in there. That's still -3. Now I can take away 2. Oh, look at that. That leaves me -5. Right? So it's the physical act of doing that. And so we just play with that for a while just to get used to it. Now, what's the hope here? What other arithmetic problem does this remind you of that's going to give the same answer? Yeah, so we could say, well, doesn't this look a lot like, at least in the end, -3 plus -2? Because that's going to give me my -5. Now, this is going to have a totally different picture if we're modeling it, but they do have the same answer. This idea, this connection right here, leads to an algorithm. Let's do this again. So what's our algorithm for subtracting integers? What's our process? Are we always going to draw these pictures? No, the pictures of the model, right? If somebody says to me, all right, so now I need you to do -273 minus 121. I'm not going to draw that.
100 blocks.
I could whip out those blocks. I don't want
What about
I'm lazy.
the
inherently lazy.
grouping?
What's that?
Grouping?
Grouping? What do you mean grouping?
Like-
How would you do this?
I would change it to a plus sign,
You would change this to a plus sign?
make them both positive, because then you use the, okay, they're double.
Oh, wow, we have different algorithms going on. Okay.
She's just
slightly
real.
different.
Okay. So let's okay. So you would do what? I'll get back to you, Christian. You would leave that -273,
Yeah, and
And you
add.
add -121?
Yeah.
So you're changing subtraction to adding the opposite. Okay. Okay. So that is one algorithm for subtraction. Close enough. Subtraction can be rewritten as adding the opposite. Yeah, so that's what we're doing there. Now, Christian, you got a slightly different algorithm going on in your head. You want to tell me about it?
Slightly different. It's just make them positive and you add them together, because oftentimes when someone looks at the negatives, they have to think of, moving the number around way too much, or I have to take away that from this. When they see it as positives, it's a bit more encouraging, and that and you just put the whole negative sign next to it. They're both negative.
So you're doing something like that. So they're both, basically you see a negative and you're seeing that as a negative too. And you're saying, I'm just combining two numbers and calling them negative. That's a slightly different process, right? An algorithm is just a process. So again, there's many different processes for doing this. Okay. So, question. Is this, so Christian gave us an alternative, but how many of you would say this is the algorithm for subtracting integers? That you always add the opposite? We got a couple hands up that say yay. Adrian's like, I think so. Pat thumb. Minerva, no, not the algorithm. Okay, Minerva's at the center. Danielle, you're off the
So
quiet
that's not the
there.
algorithm. What is the algorithm?
Wait, what
Okay.
about the one that like you put the big number on top, then the square, empty square, and then the number?
Oh, the lattice. We use that for addition and we use that for multiplication.
Okay.
I'm pretty sure, I don't recall a lattice subtraction. What's that?
You can't do this for positive and negative numbers.
We should be able to.
Let's
shouldn't you?
try it.
You can do it for multiplication with an extra twist. My mind is not catching on to lattice, the sign of addition. So we'll come back to that. So let's explore, is this the algorithm? So I'm just going to write another problem. How about 5 minus 3? So rewrite that as 5 plus the opposite of 3. Is that how you all would do that?
No, I'm just.
You just do 5 minus 3, right? Okay. Don't like that. How about 3 minus 5? How many of you would rewrite that as 3 plus the opposite of 5? You, Greg, would. Okay. Minerva, maybe? You would. Adrian? No? Kelly? Depends on the day.
Someone's like.
Oh, hello.
Hello.
Sorry, I don't have the camera on me right now. I could, let's see.
That's fine.
How do I do that here? Oh, there we are. Hello.
Hello.
Everybody, say hi to Debbie.
Hello.
Hi, Debbie.
Okay. All right, so we'll catch up here in a sec, Debbie. I'm going to switch back to the screen. All right, share. Okay, so Debbie, we decided since we got cut off last term, we missed a day, to review a bit of chapter 5 in a little more detail.
Okay.
So we're just going to play around with that today.
Okay.
So you didn't miss much. I reviewed the charged particle model and the chip model, and we talked about the number line a little bit.
Okay, perfect.
And I think I have, this is being recording, but it's probably long and boring. I think I have a shorter recording on my YouTube channel.
Okay.
Okay, so let's see. So we were just discussing algorithms. How many people would choose, when given this problem, to rewrite it that way? And we have mixed opinions on that. So when I see this, I say, okay, there's 3, and then I lost 5. So I lost more than I had. That reminds me of a negative answer. Now, that's just because I've done a shitload of these problems. I'm used to it, right? Kids are going to have a harder time with that. They will notice that, oh, wait a minute, I know how to do 5 minus 3. But isn't trading their places kind of like the opposite?
Mm-hmm.
And doesn't opposite come in nice here? Well, yeah, it is the opposite. It's not 2, it's negative 2. So that kind of falls in nice. So we can play on that. Kelly? You think about the positive version and then switch it? Okay.
Or you can just tell them you had $3. You borrowed $3 from somebody, and then you borrowed from the same person $5 more.
Wouldn't that be 2 negatives?
Oh,
Oh,
so,
no,
so
you-
you're describing negative 3 minus 5.
No, sorry. If you take, say you had $3,
Yeah.
and then you borrowed 5.
Yeah.
So you owe somebody
2.
2.
Okay.
So you're negative.
Yeah, so you can talk about gain, loss, borrow versus have. Yeah. That's definitely a good way to do it. And those charged particles can help with that idea too, to reinforce that idea. But the thing is, although we say, we do often in math classes say this is the algorithm for subtraction of integers. The thing is, based on our experience with whole numbers, there are times when we decide not to rewrite it. We like this one better. There are times when there's mixed opinions. Some people like writing it this way, some people like rewriting it that way. Is it a good idea to show kids multiple ways to do it? It is, but that's the blessing and the curse of math, because what's going to happen is if you just go one way, a lot of people aren't going to get it. And they'll complain. My teacher showed me and I didn't get it and it didn't help me. Oh yeah?
Wait for that phone call.
Who's the teacher? Who is it? Hopefully it's somebody I had in this class before. They all have seen it. Let's see.
What's the college math?
There are some books that have that in it these days, the lattice multiplication. So, shit, I forgot what it was. Debbie, can you hear me?
I can, yes.
Okay. I'm using a different mic today, that's why I asked.
Oh,
Okay. Oh, the point was we selectively decide when to apply the algorithm and when not to apply the algorithm. But in order to do that, you have to have a lot of experience. And that's one reason playing games with chips or charged particles can help gain that experience. When is it okay to try and rewrite it? When is it easier not to rewrite it? It kind of depends on the problem. So let's see, some other things. I'm going to go to the internet quick. One thing I asked you to do last term, at the end of the term, on a day off right before the final, was to look up an algorithm for addition of integers. So I'm going to go to the internet and see what I can find. Addition, rules. Are rules the same thing as an algorithm?
Explain the why.
The answer is yes, rules are the same thing. So remember, an algorithm is just a process, a series of steps. Which rules are two? Often. The rules for adding integers. Okay, so let's see. Images for rules of addition. Huh? Or math goodies, that's going to be a fun place to go. And mathgoodies.com. Okay, so they're showing number lines. Let's do it out here. Positive and negative. Oh, interesting. They have, let's blow this up. They have a rule for the sum of two negative numbers. They have a rule for the sum of two positive numbers. And how to add a positive to a negative, a separate rule. Yeah. And that's pretty typical when they get down to the rules of adding integers. They break it down into, well, if they're both positive, do this. If they're both negative, do that. If one's positive, one negative, well, then it depends. Right? But the bottom line is, and this is the interesting part, let's blow this up a little bit more. And this is where students are going to get baffled. Find the absolute value of each integer. Okay, I can do that. Subtract the smaller number from the larger number you get in step 1. Okay, and then the result from step 2 takes on the sign of the integer with the greater absolute value. How many people are lost? You all got that? Bang, done. Okay, so now you can demonstrate that. So I'm going to give you a problem. Let's say, how about, let's see, we need a positive and a negative, and we're adding them. How about 3 plus negative 7? So see if you can demonstrate that algorithm, that set of rules, with 3 plus negative 7.
-4.
Okay, so Debbie's got -4. You sure you followed those rules? You didn't use your calculator?
Right.
I'm just messing. All right, find the absolute value of each, and then subtract the smaller from the larger of the numbers you get in step 1. Then the result from step 2 gets the sign of the number with the greater absolute value. Okay, so I'm pretty old, and I can usually deal with multi-step processes up to 3 in my head. Some days. 5th, 6th, 4th, 5th, 6th grade, how are we going to do here? They're going to get those 3 steps like bang, boom, let's move on, we got it. No. It's going to take a while. Okay, so let me try that. So 3 added to -7. Okay, so it said find the absolute value of each. That was step 1. Okay, then take the smaller from the larger of those numbers. So that means take 7 minus 3. Okay, that's 4. So again, this is step 1. Right there, this is step 2. Step 3 says the 4 gets the sign of the number with the biggest absolute value. While the absolute values are here and here. Which one has the bigger absolute value? The 7 is the bigger absolute value, so the answer gets what sign? A negative sign. Oof. Is that really the algorithm? Is that what we do usually for this problem? Okay, so Christian says technically, some people say no. So let's just do it again for a different one. Let's take 5 plus -8. Okay, so here's what goes on in my head when I see that. Positive and a negative, that's really a subtraction problem. And so I really want to know what is 8 minus 5, but I'm subtracting more than I added, so the answer must be -3. So I think this, and I write that. Is that something similar go on in your head? How many people look at this and see, oh, I need to subtract? Raise your hand. Okay. Raise your hand if you really in your head do 8 minus 5. And then just call it -3 because you know it's the wrong order. Okay, I do. Oh, you raising your hand over there, Debbie? Sorry, I wasn't watching.
No, it's okay.
So how many of you look at that and say, oh, that's really 5 minus 8, which is -3? Anybody think that? Maybe, kind of, sort of. Depends on the day. Sometimes it's this way, sometimes it's that way. Depends on the, eggs in the morning, coffee, or someone's pissed me off recently.
Yeah, let's see what it makes me. I think I'm 8 in the hole on that 9 to 5 too.
Okay.
That's how I think of it too.
How do you get the 3 out of that? I get what you're saying. Yeah, I'm 8 in the hole, but that brings me up 5. So where's the 3 come from?
What's left over?
How do you get what's left over? How
So
do you
that'd be
calculate
like-
left over?
That'd be like you have $5,
Yeah.
but you have to give somebody 8.
Okay. You have $5, but you got to give somebody 8.
So
Okay.
that'd be like the subtracting.
So you actually do subtract in your head to get the 3,
Okay.
right? Is it possible to think about it. Can you really do this without subtracting?
No.
No, we don't. Okay, there's 1 or 2 reasons. Well, our brain's just wired that way, or that's just the way we were taught to do it. I tend to think our brains weren't wired that way. We were trained to do this earlier in life, and that's just the way we do it. It just becomes a subtraction problem. Whether we think about gain or loss, positive or negative chips, we see 2 numbers that we're combining, one's positive, one's negative, and ooh, I gotta subtract somewhere in there. Now this one, I mean, we're so used to small numbers like 8 and 5, 3 just pops up as a related number. Remember we talked about fact families before? Just a reminder what a fact family is. I know that 3 plus 5 is 8. So I also know that 5 plus 3 is 8. And I also know that 8 minus 5 is 3. That's the 4th fact. 8 minus 3 is 5. Okay. Those are beaten into us by experience. And so when we see an 8 and a 5 with subtraction and addition, 3 is a common number that pops up in there. So I was going somewhere with this. Oh yes, okay. So let's do this again. Let's take 73 plus negative 182. Come up with an answer without a calculator. Minutes.
Negative 109.
Answer. Happens. 109? Sorta, kinda? Negative 109, yeah, I gotta give it the right sign. But really, I got a subtraction to make that happen. And usually when we subtract, we put the big number on top and the little number underneath. That's just the way we write things down, because that's another algorithm that was beaten into our brains. So it doesn't explain why, it just allows us to come up with an answer. But it's a good idea to try and give some physical models to give students an intuition about how to do it, and then that'll help later in coming up with answers. So we think the answer is negative 109. All right, so I think that's enough with subtraction and addition for now. Let's talk about multiplication. Go. What are some multiplication models from last term? Lattice. Oh, that is an algorithm. Algorithm is a process, it just gets the job done.
Wait,
A
no.
model explains why.
The lattice is where you put the box and then cut it in half, right? Yes.
Yes, the diagonal cut.
Yeah.
Yes.
So what I was saying was like,
So
what
just a reminder, let me get a new page. So lattice is like if I wanted to do 23 times 15, I
Yeah.
would write it like that. And
So-
then 3 times 1 is 3, 1 times 2 is 2, 3 times 5 is 15, 2 times 5 is 10.
and then you
And
add
then
a
you follow the
diagonal.
diagonals. 5, 4, 3, so the answer's gotta be 345.
Okay, so I
Yeah.
go backwards, but
And that is an algorithm. It doesn't explain why the answer has to be 345, it just comes up with an answer. So model is like,
With the group,
what's that?
the groups in and the partition.
Those were division, groups in and partition were division.
Oh, okay.
Groups of was multiplication. So that was the most basic one. The set model for multiplication, we call it the group cells model.
Repeated addition.
Repeated addition was another one.
Base times height.
Base times height are the area model
And the array.
and the array model. Those were our main models right there, yeah. And I like groups of the best. You can kind of make repeated addition work. It's a lot like the groups of. So just a reminder, 3 times 2 means I have 3 groups of 2. Okay. Answer's got to be 6. There's 3 groups of 2. Okay. 1, 2, 3 groups of 2. Now I happen to draw them in an array, try to ignore that, so I can't help myself. Sometimes I need. All right, so the question is, can we apply, now that was whole numbers, can we apply this to integers? Okay, well, at the moment, we're using the charged particle model. So we have this guy as a positive, and this guy as a negative, and put them together to get a 0. So would I be able to do 3 times negative 2? 3 groups of negative 2? Could we draw that? All right, well, let's see. Well, here's a group of negative 2. And here's another group of negative 2. And there's another group of negative 2. That seems to make sense, doesn't it? How many do I have altogether?
6.
Negative 6. Does that match what you thought this meant before you saw the charged particle model in this class? Yes. Yes. Oh, thank you. All right, so that works. All right, that's cool. Multiplication is commutative, yes or no? Can I switch them and still be okay?
Yes.
2 times 3 is the same as 3 times 2?
Yes.
Absolutely. So can we interpret -2 times 3?
Yeah.
Okay, so that would mean I have negative 2 groups of positive 3. What does it mean to have -2 groups? I know what it means to have 2 groups. Not sure what it means to have -2 groups. Oh, shit. Yeah, this is a problem?
So then,
Is anybody else struggling with this?
Yeah.
Hillary's not. She's got an idea.
no, I have an idea, but
Okay,
it's
tell me.
still confusing.
Okay.
So then, with the not whole numbers, which,
Integers?
yeah, okay, so using integers, you would not be able to use the commutative property.
So it is multiplication still commutative for integers. So is -2 times 3 the same as 3 times -2?
Yes, it's the same.
It is, okay, but then we're struggling with that with this model. Because we have to figure out what the heck does that mean.
Yeah.
Okay, so, well, a model is a way to physically interpret reality. So we just need to find a physical interpretation for that. Christian, what idea?
My thought would be 2 groups of 3 and replace them with negative signs.
Replace them, okay, so replace them with a negative sign. What else does negative mean to us?
Negative signs.
Take away.
Take away. What if we replace negative with take away? Could we take away 2 groups of positive 3
Because then we would just have 2 groups.
and see what happens? Let's try it. So let's rewrite this as take, so Kristen, you're on the right track. Hillary helped cement it. Take away 2 groups. That's groups of positive. From what? Usually we take away from something. What do we have to start with here?
So would you do that?
Nothing, really.
Would you add in the?
So we're starting with nothing. So we have to somehow represent nothing, but still be able to take away 2 groups of 3. Okay? Well, here's 2 groups of 3, but that's not nothing. That's 2 groups of 3. How would I make that nothing?
Negative signs.
Throw some negative signs in with it. What's the net value of that charge? It's 0, right?
So you'd have to add in.
Is it possible to take away 2 groups of positive 3 here?
Yes.
Totally is, right? Okay, so let's try that. So let's see. I need to take away this group and that. What does that leave?
-6.
Is that an appropriate answer? Cute, we did it. We found a way to interpret it. Yeah, so if there's a negative out in front with the first number, that negative means take away. If there's a negative with the second number, that just means it is a negative number. Try that one more time to see if it works out. That's kind of weird, but it's the way it works with the charged particle model. Okay, so how about, let's try -2 times -3. Okay, so how do I interpret the first negative again?
Take away.
Take away. Okay, so this literally means take away 2 groups of -3. And we're starting with nothing. So we have to create 2 groups of -3 out of nothing. Okay. So here's 1 group of -3. I should balance that to be nothing. There's another group of -3, and I should balance those so the net charge is still nothing. So this is where we have to start. Start with nothing. A 0 charge. Now can we take away 2 groups of -3? So let's switch colors. Geez, that's a lot of colors. That one, okay. So let's see, that one, divide. What does that leave? Positive 6. Is that appropriate? Okay, so what's the alternative to modeling it this way? The alternative is to just demand that when you multiply two negatives, the answer has to be positive. It's okay. You can be a demanding teacher. You should be a demanding teacher. But if we can model it somehow, it's not a bad idea to try. So somehow modeling this can lead to an algorithm, or you just state the algorithm. So here's the algorithm for multiplying integers. Algorithm. There we go. Multiplying integers. What's another word for algorithm?
Rules.
Rules. What's another word? Steps. Another one? Ooh, could be formula. Yep. A word that starts with P, R,
Procedure.
C. Procedure or process. Yeah, so an algorithm is a set of rules, a set of steps, a process, a procedure. It's all of this. We just happen to be fond of that word math, algorithm. I think it's because people have not corrupted that word like they've corrupted other words like process and procedure. It sounds intimidating, but it sounds like I can do algorithms. Doesn't that sound like awesome? Like you should get a badge for that.
It sounds like there's
Little sash.
Sector.
something.
What's that? Sounds what?
It just sounds like something smart.
It is smart. You should be proud. I'm saying, I keep thinking we should have sashes and badges for this class. Master of algorithms, master of models. Anyway, so here are the rules. If the numbers are the same sign, anybody want to finish this for me? Then,
They hold that sign.
no,
They're going to be opposite.
no.
You're gonna add them together and keep the sign.
No, we're doing multiplication.
Oh,
Oh, shoot.
Positive times a positive, negative times a negative.
All positive.
The answer is positive. That's it. Yeah. So if the numbers are the same size, the answer is positive.
Okay.
2. Well, let's see. If they're not the same sign, they are not the same sign. They are opposite sign. So if the numbers are not the same sign, oops, wrong sign. Then the answer is negative. That's kind of different from the algorithms we did back in Math 211, like the lattice and the expanded algorithm. This is just a couple rules to follow as opposed to this complex procedure. Is that all I need? No, let's see. What's that?
We need more problems.
I just had that one. Yeah, if the numbers are not the same sign. E. So let's just think about it. So somebody says to multiply negative 21 by negative 25. I mean, I already know how to multiply 21 by 25. I just need to know whether the answer is positive or negative. Agreed? That's the big problem. That's the new twist to integers compared to whole numbers. So I know the answer is positive, and now I just multiply 21 and 25 with my favorite other whole number algorithm. Whether that's lattice. I know Hillary's real fond of that Russian algorithm.
Is that the one that I couldn't figure out?
No, that was expanded maybe?
Yeah.
I think he did the Russian, okay. So not much of a big deal. So just some other things. You have a couple of choices. You just tell students, that's the way it is, love. Deal with it. Christian, you happy with that?
Yeah.
Christian's happy with that.
I'm content with that.
You're content, Hillary?
I'm not.
No, Hillary is not content with that. She's like,
Well, I've had a
I want
teacher
a
that's
reason. I
done
just
that,
don't want
yeah.
you to say it is. Why? Because I know you hate that when your parents are like, you're grounded. Why? Because I said so. What do you mean? That's not fair. Why is this? That's because I said so. So let's look at some other reasons that can kind of work into that. How many find the charged particle thingy kind of freaky? Anybody? Adrian definitely thinks it's freaky.
Yeah.
That's okay. It's different, right? But here's the bottom line. You have way too much knowledge in your head. You just know how to do it. And we can't just tell people, just do what I do. They don't have
Like,
experience.
well,
in it.
But you have
What's
to.
that?
Can you put that in writing? Because I have to know.
Oh, sure, yeah, you can absolutely.
Can I have that on paper?
But it's
Yeah.
also
Yeah.
not ideal, because like you said, if you're taking 273, if you're taking your large numbers, you can't.
Yeah, when we first start working with integers, are we really going to throw big numbers in there, or are we going to start small?
We start small.
Yeah, so that's the thing. We start with numbers like 2, 3, maybe get up to 5, right? And we draw these pictures to kind of get the flow of it. Like, why should it work out this way?
But you have to also think
Now-
about how this is a way to help them work.
It's to help them understand. So there's some kids that you give them a rule, they follow it. They eventually remember all of the steps. There's other kids that aren't so good with steps, they have to have a picture in their head about how it works. And it's just all our brains are different. And so some kids are going to just be fine with rules. They're going to love it. Other kids are going to need these things to do it. The rules aren't going to be enough. They'll mix the rules up because they don't know why they should be using that rule. And that can be a problem. So here's some other models that we can use to talk about this. So we can use patterns to model this. So patterns as numbers. And then I'm going to shut up after this example because we're out of time. Let's see. 3 times 3. We all know that. We studied that last year back in 3rd grade. 3 times 3 is 9. And some of us still have to count on our fingers, and that's okay. 3 times 2. 6. Okay, good, good, good. 3 times 1. Great, beautiful. 3 times 0.
0.
Okay. So these are multiplication facts. We have a multiplication table that this is in. The kids are getting used to this. Does anybody see a pattern in this column here?
Subtracting by 3.
Yeah, we're dropping by 3 each time. We're subtracting 3 each time. Okay, so that's cool. So I could draw that pattern in here. Drop by 3. Drop by 3. Drop by 3. Now kids got to the idea that, hey, the number line keeps going. Isn't that cool? And we can continue to drop by 3. Where are we going to drop next? Yeah, we're going to end up at -3. Okay, what does -3 mean? Okay, well, we have charged particles. We can talk about that. We've talked about gain and loss with the kids. One model that hasn't come up yet, and this is totally my fault, it's damn cold out, isn't it? Celsius scale, anybody know what the temperature is?
Too cold.
It's minus something, right?
I'll tell you.
32 degrees Fahrenheit is 0 Celsius. And so it's in the negatives right now in Celsius.
It's only 3 degrees Celsius.
It's 3? It's above freezing? Get out. So it's like
Snapchat
what,
says it's
39 degrees out?
26 degrees.
26 degrees would be a negative Celsius.
Yeah.
It doesn't give you Celsius there?
No, it does, but it says 3.
Why?
It's just Snapchat.
It's just Snapchat, but it's so trustworthy.
Snapchat is full of shit.
My own kilometers.
Okay, so,
Miles per hour.
so what's a good idea, if possible in a classroom in the wintertime and you're doing science numbers, have a thermometer outside so you can check the temperature. And if it's not near a window, just have it outside, and every day have the kids check the temperature. Right? Especially when it gets below freezing, so that we can see these negative numbers. Okay, so that's another application we can use. All right, are there any other patterns I have on this board here? Back to this board. Let's see, 3, 3, 3, 3. What's the next number in the first column?
3.
3, good guess. Okay, so we can nail that one. Is there a pattern in the second column?
Yeah.
Yeah, 3, 2, 1, 0,
-1.
probably -1. So here's a pattern that shows that 3 times -1 ought to be -3.
Chapter 5 to be 4 or something.
Yeah, it's one of those, yeah, the end of
The last one
chapter.
that we turned in.
Yeah, the last thing you guys turned in. So I just wanted to go over that a little bit. And then we can keep going. So then we can say, oh, does this tell us what 3 times -2 is? And yeah, we've dropped by 3 again. -3 minus 3 is going to be -6. So we can use patterns to generate these things too. So if you're freaked out by the charged particles, they hurt your head, there's an alternative. Now, it could be the curriculum your district chose has charged particles in it. Then you might want to do it. You might be told you have to do it. Depends on your district. Sometimes you might have a choice on how to do it. A lot of teachers supplement the materials they have. It just kind of depends. All right, so we're out of time for fun with integers today. So there's going to be nothing official for chapter 5 to do. I just wanted to go over this because I felt like you guys got shortchanged last term. We're going to pick up in chapter 6 on Wednesday. Is that what we meet again?
Yeah, so we don't have any activities due?
No, there's not going to be any activities due for chapter 5. No, we'll pick up for real. So hopefully sometime today or tomorrow, the real Math 212 course will appear on eCompanion. I'll get the dates fixed.
I was thinking like you don't really like that one anyway, so.
I hate eCompanion.
Yeah, so you had
Yeah.
like made up your own website. That's what I was thinking. I'm like,
I really, really wanted to, but there just wasn't enough time over the break to do that. That is my summer project.
I was thinking you made up our own website.
I'm going to make a new website for this course. The other thing, I want to make it free so you don't have to pay for all these books. Sorry you guys are missing out on the free stuff. If my summer goes well, that will be a reality next year.
One of my other teachers did that.
What's that?
We're the guinea pigs until then.
Sort of, yeah. I've had lots of guinea pigs over the years. Thank you for your help. All right, so actually, I'm going to switch over and talk to you, Debbie. Oh yeah, help yourself with those toys. Hang on, Debbie.
But it says physical geography.
Here.
Oh yeah, that's not the right one.
So I went during class.
So just to catch you up a little bit, somehow the wrong course got put in VMCC Online, and I asked that be fixed. So hopefully sometime later today or tomorrow that will be. As of earlier this afternoon, there was nothing in there for you guys to do. And so we'll see that should be fixed today or tomorrow. We'll officially start off in chapter 6, but again, I felt like reviewing chapter 5 stuff because we kind of got shortchanged at the end there and rushed through it. And otherwise, the course is going to be pretty similar to last term. You'll have workbook activities, online activities, and tests will be part in class partake only.
All right. Sounds
And then
good.
You found this email link, okay?
Yeah, I had to download it again for some reason. I'm not sure why.
Oh,
And approve it all and everything. So
okay. Well, hopefully that doesn't happen every time. It shouldn't. What web browser were you using?
just Internet Explorer, but I had my laptop in the shop and they like removed some stuff. So maybe that was just something that got removed and then.
Yeah, they probably updated Internet Explorer and it lost track of the Chrome plugin. And if you ever run into any troubles in Internet Explorer, you might need to switch to Chrome. But if it worked today, it should keep working okay.
Okay.
So let's see. So what I'll do is each day I start the class, I'll invite you to join. I don't like this, I let this recording go on for an hour and a half. And so I usually won't do that. I'll usually stop it and then restart another one. And each time I restart, I'll try to make sure I invite you, but every once in a while I get distracted. And so if you think there should be a session and you're not seeing it, do you still have my cell phone number?
I do.
Okay, so I'll have my cell phone in class. Just give me a ring if there's a problem and I'll correct it.
Okay,
All right.
sounds good. Thank you. All
You're welcome. All right, so I will see you on Wednesday. Have a good couple days till then.
right, you too.
All right, thanks. Bye-bye.
Bye.